consider how those modifications impact other observations. The second reason that I've been interested in has to do with more theoretical motivation. And that's we know that Einstein's theory can't be the full story because gravity cannot be included with the other fundamental forces in a consistent theory. It can't be quantized. So it's interesting to consider modifications of general relativity that might be coming from some more complete theory at higher energies. And one of the generic results of modifying gravity, modifying general relativity, is that we create a new degree of freedom in the gravitational sector. And it's this new degree of freedom, the title of my talk, that would allow us to connect local dynamics tests of gravity on small scales to implications of these theories in cosmology.
There are no good reasons why it should make mass from particle physics point.
You mean this new degree of freedom and so forth, right? Well, I mean, I'll get to some of them. So essentially, the two, hopefully two topics that I get to today are going to emphasize how various modifications of general relativity produce new degrees of freedom, and how we can exploit these new degrees of freedom to measure processes occurring locally, and then extrapolate that and understand cosmological implications of these two modified gravities. So the first theory that I'm going to talk about is Chern-Simons gravity. And I'm going to present a recent result, the first ever observational constraint to this modification of gravity. And it appeared in this archive here. It's in press for PRD. And this is work that I've done in collaboration with Adrian Ericchek, Robert Caldwell, and Mark Minkowski. So first, some motivations as to why we might want to consider this Chern-Simons gravity. So first of all, this is the second point, second reason we might want to consider modified gravity. This Chern-Simons gravity represents a higher curvature correction to the Einstein-Hilbert action. So that's one reason that it might be interesting. It actually does have a connection to possible completion of gravity in inconsistent theory with the other fundamental forces at higher energy. It's also interesting because it highlights how we might actually seek out to test whether parity is violated in the gravitational sector. We know that it's violated in the weak sector, and there aren't any tests that conclusively rule out that it might be violated in gravity as well. And introducing this Chern-Simons modification introduces parity violation. And two places that you might look for this parity violation that have already been worked out are in polarization in the CMB and in gravitational wave detection, both of some stochastic background of gravitational waves, as well as gravitational waves coming from some localized source. So as I'm going to talk to you now, there are some other tests that we can do to look for parity violating effects of gravity, just looking at the orbits of satellites around the Earth. The third reason is that this Chern-Simons gravity has been shown to participate in a mechanism that leads to matter and antimatter asymmetry. So it has some interesting implications there. And then last, one can show fairly generically that including a Chern-Simons term, as I'm going to show you on the next slide, is a natural consequence of the effective 4D string action for a large class of string theories.
But it will be normalized on the string scale.
It will be normalized on the string scale.
Now I prove that.
Right. So in terms of the actual energy scales you need to get to, any test you can do with satellites around the Earth is not going to approach those energies. But it is a first step towards looking at ways, gravitational ways of looking for this term that might, in the future, with gravitational wave detection, something like that, get you closer to that energy scale. Okay, so here's the definition of the modification. And I'm just going to go through each term here and just identify what they are. So the first term is just the usual term in the Einstein-Hilbert action. The second term is the meat of the theory. This is the Chern-Simons term. And you can see here the Chern-Simons term is just a contraction between two Riemann tensors and the Levi-Civita tensor. Multiplying this RR tilde term, RR dual, we have a scalar field theta. And in order to write this term in a dimensionful, in a proper way, we had to include this dimensionful constant, which would be related, if this were coming from string theory, to some string length. And then we also include, and this is somewhat of a novel feature in terms of the work that we've done, we've included usual scalar and kinetic potential for the scalar field that's multiplying the RR dual term there. And then finally, we just have the usual matter of the progeny. So parity is violated in this theory through this RR tilde term. And schematically, you can think of this combination here, this product of two Riemann tensors, as an equivalent case when you have a similar combination of Maxwell field tensors as just a combination between the gravito-electric field and the gravito-magnetic field. So we can see, because the gravito-magnetic field appears here, that this is actually a pseudoscalar. So assuming that theta is a normal scalar, this term will violate parity. And another reason that it might be interesting to consider such a coupling between a scalar field theta and this combination RR tilde is that you can think of this coupling as coming from some approximate shift symmetry. So one can show that this RR tilde term that I've defined here can just be written as a divergence of some current. So that if we were to take theta and just translate it by some constant value, the term that's introduced into the action is just a surface term and vanishes.
Well, then you should erase your potential.
Then you should erase, so well, that's why I also put approximate shift symmetry. So it could be broken a little bit by adding some mass. Right.
So it's
That's where strict symmetry is.
That looks like the same as the Gauss-Bonnet term. It's totally derivative.
So it's not the same as the Gauss-Bonnet term. And although I haven't had much experience with the Gauss-Bonnet term, this is going to arrive to give you a third-order differential equation, third-order gravitational field equation, which the Gauss-Bonnet term.
So the Gauss-Bonnet term is also a total derivative, right?
The Gauss-Bonnet term is also a total
I didn't
derivative.
realize there were two things.
Yes, so right. So this is different than the Gauss-Bonnet, but it also is a total derivative. And you'll see, I think the Gauss-Bonnet term would have yielded second-order gravitational field equation. So that at least indicates one of the differences. So we can take this action with respect to the scalar field, with respect to the metric, and we have our coupled field equations, one for the scalar field and one for the gravitational sector. So we just have the usual relationship. We have the down inversion acting on the scalar field, and we have this new source here, and it's sourced by this RR dual term. In the gravitational part, we can see that this G mu nu is just the usual Einstein tensor, and it's sourced in the usual way by stress energy. And we have this modification here, this tensor that I've defined to be C mu nu, and what we call it is the Cotton-York tensor. So I'm going to call it that for the rest of this talk, although it is not strictly the same as what one would usually write down for the Cotton-York tensor. It's a bit different. There are two interesting parts of this modification. One is the fact that you always couple to the derivative of this scalar field, and this just reiterates that approximate shift symmetry. So if I just change the scalar field by some constant, it's not going to affect the gravitational field equations. And the other is that this derivative operator, in one term, will act on the Riemann tensor here, and that's going to introduce third-order derivatives of the metric into this field equation. So we write this down, and our usual gut reaction when we have some new modified period of gravity is to say, okay, we have two spacetimes that we think we know very well. We have Schwarzschild and we have FRW. One of the interesting consequences of the structure of this correction here is that it can be shown that this correction, this Cotton tensor, C mu nu, will vanish for any spherically symmetric spacetime. So what that means is that our usual tests of gravity in Schwarzschild geometry are not going to be able to distinguish between Chern-Simons gravity and Einstein gravity.
And that is because you don't have enough vectors to contract to that? Or?
I don't know. I guess, I mean, the way I've thought about it is it just has to do with the particular way in which a spherically symmetric metric, well, in some sense, it doesn't produce a gravito-magnetic field. Right? I had said before, you can think of this combination here, but the combination RR dual, which is related to this C mu, as just a product between an electric and a magnetic field. So spherical symmetry can't produce, so in some sense, right, there is no preferred direction. We have to break spherical symmetry in order to start to see modifications. presents an interesting challenge. What types of observations can we make in order to probe this modification? So to get to the heart of that, what we did is we linearized this field equation about a Minkowski metric and looked at what the linearized field equations told us. And so that's what we're going to just run through quickly now. So as I said, we're going to take our metric and we're going to linearize about a Minkowski metric, theta mu. We're going to rewrite things in terms of the trace reverse metric perturbation, h bar. And we're going to remain in a harmonic gauge, which is essentially just the divergence of this h bar branch. And we're also going to consider the case where the scalar field theta is just going to depend on cosmic time. And we're going to neglect any contributions from the acceleration from the second derivative of theta with respect to t. In order to aid our understanding of the physical content of these linearized field equations, we're going to write them in an analogy with Maxwell's electromagnetism. To do that, we just define a 4-vector potential in this way in relation to this trace reverse metric perturbation. We have a 4 current, which is just related to the stress energy tensor in this way. And we define in the usual way, in terms of this 4 potential, a 4-vector field, an electric and a magnetic field, the gravito-electric and magnetic fields. So with these definitions, we can write down the linearized field equations in analogy to electromagnetism. And let me just run through the results. So Gauss's law remains unchanged. Our gravito-electric field is sourced in the identical way that avoided general relativity. And this, in some sense, can be understood to be a consequence of the fact that if you just had spherical symmetry, you would have the same gravito-electric field in Chern-Simons gravity and in general relativity. Faraday's law is just a consequence of the way that we define this gravito-electric and magnetic field, so it remains the same. And we also have no gravito-magnetic monopoles. Again, just the way that we define this field B. The final law, and this is where we do find a difference, is Ampere's law. So here in Ampere's law, we have this difference here where I've defined this Chern-Simons mass, and it's defined in terms of the dimensional parameter L, as well as the first derivative of the scalar field theta.
So you said there is no theta double knot, is that what you said?
So there would appear some, well, so in this expression in and of itself, there is no theta double knot. That is exact. When we go about solving that equation, we neglect second derivatives of theta.
And what is J?
So J is just the 3-vector associated with the 4-vector current. So it's the mass current in your system. So one interesting consequence, so we can write our linearized field equations in analogy to the Maxwell field equations in electromagnetism. But the analogy goes even further. And that is, if we just look at the geodesic equation for some massive particle, one can show that its acceleration is related to the electric and gravitomagnetic fields in a way that's, again, analogous to Lorentz force law. And we're going to use this later in trying to actually probe consequences of Chern-Simons gravity.
Is there a 4 there? Oh.
Yes. So there's a 4 there, and that is the difference. That's why it's not exactly the same. But you can either define the field equations to look, equivalent to Maxwell field equations, or you can define the Lorentz force law to be the same. Okay. So what we found by looking at these linearized field equations is that our gravitational Ampere's law is the only equation that's modified. And again, this makes sense given the fact that Chern-Simons gravity presents no correction for spherical symmetry. We need to actually produce some non-zero mass current in order to produce a gravitomagnetic field and to see modifications coming from Chern-Simons gravity. So the question is, where are we going to find a mass current to generate a gravitomagnetic field? And there's one big mass current that we're sitting on, and we actually have very precise information on satellites that are orbiting this mass current. So in our calculation, we calculated the gravitomagnetic field for a rotating spherical body that it will take to be the Earth. So in that case, we can write down this mass, the 3 vector, this 3 current, in this way. We just have a constant density rho. And then we solve the Chern-Simons modified Ampere's law for a static case. And before I present the solution in a graphical form, I just want to go through some of the details of this equation.
Okay, can I ask you something? Sure. So you have RR dual times theta, and theta has to move, right?
Theta dot has to be
So
non-zero.
what source is theta dot cosmologically?
Exactly. What we're doing is, we haven't actually built any specific model for theta dot, but what we're imagining is it's something like a quintessence.
So theta dot is really small then, right? Because
So
you know that you cannot be larger than the square root of
The Hubble curve. Yeah, no, absolutely. So if you were actually to just use a simple quintessence model, you would find that theta dot's very small. And I'll get to that in a little bit. Just mentioning that we haven't built a specific model, but if you can find a model in which you have a cosmological scalar field that's moving fast and doesn't violate any energy density conditions, that would improve our constraint to this fundamental parameter f. Of course. So looking at this equation, there's one thing that we can see. If this mass term, MCS, goes to infinity, then this term here is negligible, and we regain the usual relationship that we would have in general relativity. So what we expect and what we find is our solution in a limit that this mass goes to infinity regains general relativity. So we're going to be placing lower bounds to MCS with our observations, if our observations agree with the general relativistic prediction. The other thing to note is that in order to solve this differential equation, we have to impose some boundary conditions at the surface of the Earth, in this case, or of our spherical mass. And in order to do that, we need to use some of the homogeneous solutions to this equation. So the homogeneous solutions turn out to be spherical Bessel functions. So the full solution for this gravitomagnetic field with the Chern-Simons modification has oscillatory behavior. And then finally, we can actually see in this equation where the parity violation is occurring. And we can see that because we know this gravitomagnetic field is a pseudovector. So under parity, it's going to flip sign. But this term here, since it's a curl, will remain the same. And in the end, what we find is this term flip sign under parity. And one other thing we can note here, if we take the opposite limit where this mass becomes large, we can see one of the consequences of this equation, if this were the dominant term, would be to produce a gravitomagnetic field in the same direction as the mass current. And that's going to be the telltale sign of parity violation with this effect.
Tristan, can you turn your microphone?
Turn it up.
On.
Oh, it hasn't been on.
Yeah, sorry. We're getting new open again.
Sorry.
My bad.
So, okay. So, so this is just going through how we could actually understand parity violation to be occurring if we produce a gravitomagnetic field in the same direction as the mass current. So in general, our solution is going to involve 2 different types of magnetic fields. One is the poloidal field, which is just like a dipole field, and the other is the toroidal field, which is going along the equator. And just to remind you, the force law that we have here for a massive particle looks like Lorentz force, so it goes as V cross B. So in the case of a poloidal field, we can imagine that if we had a right-handed universe, the poloidal field is going to be produced facing upwards in the direction that our right-hand rule would tell us for this mass current. And so it's going to circulate this way around the body. If we then look at the force that's exerted on a test particle that's coming in from the right here, we can see that what it's going to do is it's going to produce a force pointing out of the screen. In the case that we live in a left-handed world, the direction of this poloidal field is going to flip sign, but so is the direction of the force itself, so that we get the same result. But in the case that we have a toroidal field, if this field is always forced to be moving in the same direction as the mass current itself, we can see that we have an experiment that would distinguish between right-handed and left-handed. If we send in a mass in the same way with a right-handed rule, this force law here is going to tell us that it's going to experience a force downward, But in a left-handed world, the force is going to be in an opposite direction. So to present the solution to that modified Ampere's law, what I've written here, this is just the regular general relativistic result. We have here the three different components of the gravitomagnetic field. And we can also see that the gravitomagnetic field in the direction of the mass current is 0 in general relativity. When we then plot on top of this the result from Chern-Simons gravity, first of all, we can see the oscillations that are coming from these homogeneous terms we have to introduce to restore the proper boundary conditions across the surface of this body. And we can also see that it's producing a non-zero B phi. And this is the parity violating aspect of this field. So, sure.
Since the order of differential equation increases, then you should add some boundary condition, shouldn't you?
So the boundary condition that we have is that the metric is continuous across the boundary, and so is the gravitomagnetic field. You can work it out in analogy when working out boundary conditions in electromagnetism. You can work out what should occur at the boundary of a surface.
Correct. That's when you
Yes.
increase the order, so that there wasn't any boundary. There was a boundary condition that you didn't use, you didn't have to use, and now you do have to use. Which is that?
Well, so that is the continuity of the magnetic field in both the direction parallel and perpendicular to the surface, and it's implied by the field equations themselves. Right, but you do have to have extra boundary conditions to solve this appropriately. So with the gravitomagnetic field, the solution to this modified field equation, we then had to ask the question, how do we go about actually probing a gravitomagnetic field around the Earth? How accurately can we actually do that? And I'm writing here, again, the force law that's experienced by a massive particle. And this can be viewed, this extra term here, this B cross B, is going to be subdominant to this gravitoelectric field, which is just the normal Newtonian potential. So we can view this as some small perturbation on top of our usual Keplerian motion for these satellites. And what we do then is we look at the perturbed motion that builds up in time. We're going to perturb about a Keplerian orbit. Of course, there is motion in these satellites that's periodic, but we want to look for the motion that's actually building up in time, that's secular. And it's the same thing that we look for in the perihelion of Mercury. It's a secular effect so that that builds up in time, whereas there are other perturbations that only fluctuate and we don't have enough accuracy. We have to use a larger time interval in order to get enough accuracy to see these secular effects.
Can you go back one slide?
Sure.
Sorry, the other slide. Yeah. So this seems to say that in the limit of large little r, the second line, I don't seem to be recovering the GR result.
So large, you're saying this R here,
Yeah.
the position?
Yeah, in fact, the first 2 lines. Okay. My worry is the following, that because you have high order equation,
Right.
you have a ghost in the theory, and you might worry that if you use boundary condition that excite the ghost and therefore creates an instability that sells out towards R infinity.
So, I mean, the term definitely goes to 0 at R equals infinity. Is that? This definitely drops. This drops slower. Is that what you're saying? That's
Exactly,
GR.
and that's the correction that you're adding. So at large distances, you're not recovering GR.
So at large distances, right, at a large enough distance, this will become.
Which
I see what
seems
you're
to
saying.
say you've built up an instability at the origin which grows.
Okay, I see what you're saying.
So that relates to your boundary condition question. I would have thought that the way to solve this equation is to do it perturbatively around the GR solution to make sure you're not ever exciting that ghost.
So yeah, so if you actually sit down to do that, you find that you don't actually have the appropriate. If you just do it perturbatively, you're not able to generate these homogeneous parts, and so you don't actually have the appropriate boundary condition across the surface of that sphere of the Earth. So essentially what you find is that this gravitomagnetic field is discontinuous across that boundary if you just look at a perturbative solution. So you're right, these terms obviously occur when you're looking at the homogeneous part of that solution to that differential equation. So I'm not sure whether just perturbing around GR is able to generate the appropriate solution in and of itself. Because the order of the equation is higher, you have to include some extra boundary conditions.
Just in saying is you determine the extra derivative. Mm-hmm. When you perturb, so you need a third derivative to say what that is. You determine a normal GR solution by just you do the normal GR problem with two derivatives. Mm-hmm. You solve that, then you can compute the third derivative from that, and that gives you the boundary condition then for the perturbations as well.
Okay. Maybe I can talk to you guys afterwards, but I mean, I understand what you're saying. This definitely does become dominant at some large R as a correction.
But if it's oscillatory, then, I mean, in a way, it doesn't matter, right? It oscillates very fast, so you can, because if it oscillates very fast, then for all practical purposes, we don't see it, right? So that's one way to look at it.
Well, I guess you're right. It's not a catastrophic instability, but the worry is that as an effective theory, is pushing it beyond the regime of validity.
Yes, like linear integration theory breakdown is that. Yeah. Okay. I mean, that's why it's first thing, right?
I mean, I see what you're saying. Well, but yes, definitely at some radius that will dominate, and maybe, I mean, you're saying that indicates some instability, but it definitely, we are not looking at that regime. I don't know if that makes a difference. We're not actually at a radial distance that would start to have that term dominate greatly over the GR part. But that might, I mean, let's chat about it maybe afterwards. Okay. So just to get back to what we do once we have this gravitomagnetic field in hand, we just look at this as some small perturbation. What we're going to look at in terms of the orbit of a satellite around the Earth is we're going to measure the evolution of a parameter, a Keplerian element, known as the longitude of the ascending node. And I've defined that here. So let me just walk you through this a little bit. We have set up a coordinate system, x, y, z, with the z direction pointing in the direction of the angular momentum of the Earth. And then we have an orbit of a test particle, a satellite around the Earth that has some inclination I. And the line of the intersection between the plane of the orbit of the satellite and this reference plane that we've defined relative to the angular momentum of the Earth has an angle, and that angle is described by the longitude of the ascending node. I guess when you work with science that's been around for 200, 300 years, you start to get very long names for these things. So it turns out that if you look at the perturbations induced by this extra term, the time evolution of this longitude of the ascending node is secular. And it's actually been measured by these two satellites, LAGOS. So we have LAGOS 1 and 2. And they're two satellites that are orbiting the Earth. They look like this. So each one of these circles here is a retroreflector. And there are many laser ranging sites around the Earth that are just pointing lasers up at this thing and getting extremely precise information on the orbital motion of these two satellites. So using this information, Ciuffolini and Pavlis in 2004 have confirmed the general relativistic prediction for the precession of this line of nodes to within 10%. So we can use that confirmation in order to then place a constraint on this Chern-Simons term here. So what I'm plotting here is just the Chern-Simons contribution divided by the general relativistic result on the y-axis. And on the x-axis, we just have this Chern-Simons mass. So we can see the characteristic oscillations here. And then beyond some mass, we can see that the corrections to the general relativistic prediction are within 10%. And so we say that those have passed this particular test. I've indicated here how this scales with the semi-major axis of the orbit of these satellites, as well as the radius of the Earth. So we can see that if we actually were to do this experiment at a larger semi-major axis, we'd have more sensitivity to constraining MCS. From these observations, we can conclude that MCS must be greater than 1/1000th of an inverse kilometer, translated into energy units, that's 10 to the minus 22 GeV. Now there's another experiment that's currently flying that's hoping to measure gravitomagnetic effects, and that's gravity probe B. So this experiment has a storied history. It's been around for something like 40 years, and they're currently analyzing data from the last year. And what they have done is they've sent a satellite in polar orbit around the Earth with 4 gyroscopes that have all been spun up in order to point in a particular direction. And general relativity predicts 2 different types of precession of the spin of these gyroscopes. In a north-south direction, it's predicted there to be this geodetic precession, which is just due to the static Schwarzschild metric of the Earth. And then there's an extra precession that's east-west, that's orthogonal, that's due to the gravitomagnetic field of the Earth. And it's much smaller. It's about 42 arcseconds per year, as opposed to 6,600 arcseconds per year. But it was hoped that the accuracy of this gravity probe B satellite would confirm this prediction of frame dragging to within 1%. Unfortunately, they ran into some problems after they launched this thing. They had, I think, some extra electric charge that they couldn't account for that produced a torque and produced an anomalous precession of these gyroscopes. They're currently, I don't think they've actually released anything. I think they said by December they'll be releasing data. But to be safe, what we've assumed in our analysis is what would happen if gravity probe B were able to verify the general relativistic prediction to within 10% as opposed to their claimed 1%. So we can see I'm plotting the same thing as I did before with the LEGO satellites, just the Chern-Simons contribution divided by the general relativistic contribution. And again, on the x-axis, we just have the Chern-Simons mass. And because of this higher dependence on the semi-major axis, on the actual orbital separation, determination of this ratio to within 10% improves our constraint on this Chern-Simons mass by an order of magnitude. So we can conclude if gravity probe B were to confirm general relativity to within 10%, that this Chern-Simons mass must be greater than 10 to the minus 21 GeV.
Is there a circular orbit for this?
Yes.
Now, if you have a small electricity, then wouldn't you wash out these oscillations?
So if you had some small elasticity, the oscillations would definitely be different because you'd be probing various distances away from the source. But the oscillations themselves, I mean, the actual magnitude of the effect is not going to be.
The thing is that, yes, so you
You
have this oscillatory solution, which is spherical, in a spherical coordinates. But if you're probing different radii, then basically you're averaging over these oscillations. So
well, the actual envelope here also changes.
But what you care about is the average, probably, not the envelope, right? Because if you're averaging out the oscillations, that's when you're going to see the mean.
We average things, and the result is not any different than
you did the average thing. Okay.
We did one, yeah. I mean, essentially, the process of averaging over an orbit is.
No. But if orbit is circular, that's something. But orbit
No, I know, with the non-zero eccentricity, absolutely.
Okay.
Obviously, there's no motion in the radial direction for a zero eccentricity. But yes, we did look at non-zero eccentricities. Yeah. For these actual satellites themselves, the eccentricity is negligible. If you just put in their eccentricity into the average, they don't really probe enough. I mean, essentially, you need these oscillations to be occurring smaller than the distance away from the source. Yeah.
So also, the Earth is not very symmetric, so you take that into account, or that
Well,
doesn't matter.
So what we've done, so these, obviously the analysis, the statement that gravity probe B is going to be able to reach 1%, let's say, in measuring this precession. And this precession actually isn't a good example because it doesn't really depend on the quadrupolar or whatever other higher multipoles you can put for the Earth's mass distribution. But what we've done is we've just assumed if they say this can be measured to within 10%, then any corrections that would appear for this Chern-Simons term would be similar and would cancel out this ratio. So in our actual analysis, we did not take into account any higher multipole structure of the Earth itself. But it's not a difficult thing to do. And we expect that it would affect both things similarly, so that the ratio would just divide out. So just to recap the types of limits that I've been talking about, our current observations of the LEGO satellites give us an upper limit of 10 to the minus 22 GeV, a lower limit, sorry. And future observations may improve this by an order of magnitude. So it could be 10 to the minus 21 GeV. Now the real question is, how can we interpret this in terms of a fundamental test of this theory? And of course, in order to do this, we're talking about limits to this mass term, MCS, which is given by a combination between the dimensionful parameter L and this theta dot. So in order to refigure these constraints as a constraint to L itself, we have to come up with some model, and we leave that open to future work. It's not something that we touch upon. Then it's a very sad constraint to L. It's saying that 1 over L is, I believe, less than or greater than 10 to the minus 100 ml. Yeah, you can, I mean, of course, I did that right away. So the real question is there anything else you can put in there that would actually increase theta dot in order to then increase your sensitivity to L? But besides coming up with some specific model that would maybe improve your constraint to L, another place to look for these effects might be the double pulsar system. So here I'm just showing, obviously, an artist's view of what this might look like, including the curvature of spacetime. And these systems produce something fairly interesting when you're trying to look for how you can constrain modifications of this Ampere's law for the linearized gravity. You can just view Chern-Simons gravity as being one example of this, but you can have various modifications you can put in. So this system is a little more complicated. In the original system, where we just have the Earth spinning, that just presents one mass current, just the rotation of the Earth itself. But in the case of a double pulsar system, so two pulsars orbiting each other, you have the added current of the actual motion of the pulsars around each other. So you have to take that into account consistently. You can also just calculate in terms of general relativity that the gravitomagnetic field experienced by these two objects is going to be an order of magnitude larger than that of the Earth on these satellites. And the orbital motion might provide much more stringent constraints because, as I was saying before, in the observations of these satellites, we're forced to only look for these secular effects, these effects that build up in time. But if our observations of these double pulsar systems are accurate enough, and we can actually start splitting things up into smaller time bands, it might be possible to start to look for oscillatory behavior due to these modifications. And in particular, oscillations in the orbital separation are possible due to just perturbations to the eccentricity of the orbits. And so I'm looking into how that might improve constraints to either Chern-Simons gravity or any other theory of gravity that predicts a modification for the Ampere's law in linearized gravity. So to conclude for Chern-Simons gravity, what I've shown is the first ever observable constraints on the theory, and highlighted the fact that the production of a gravitomagnetic field that is toroidal, or a gravitomagnetic field that's pointing in the same direction as your mass current, is an indication of parity violation. We've also seen that the coupling of this scalar field, which is the new degree of freedom of the theory, necessitates model building. And there's also a question if we're actually coupling in the scalar field that's pointing in the cosmic time direction, what type of constraints can we get by looking at referred frame effects? And I've also talked about some future work where I'm looking to articulate new tests of gravity for looking at the double pulsar system and looking at implications for modifications, or looking for modifications of the gravitomagnetic force between the double pulsars. So that is the conclusion of the Chern-Simons part. There's another theory of gravity, or another test of gravity, that I've been working on. And this test is testing the universality of gamma ppn, and how we can use measurements of galaxy lens surveys to test alternative theories of gravity. So we can parameterize deviations from general relativity when measuring the lensing of light through gamma. So here we just have the deflection angle, delta theta, that we observe, and it's related to the mass of the lens itself and the impact parameter through this parameter gamma. So in general relativity, this parameter gamma is identically 1, and we have the usual lensing formula. And we know that in the solar system, we've observed Shapiro time delay to such accuracy that we can state that this gamma parameter must be less than was equal to 1 to within 1 part of 10 to the 5. So we know general relativity, the weak field limit in the solar system is very well tested, at least when it comes to the deflection of light. And it's usually assumed that this observation in the solar system is a universal statement, so that if I were to go out and somehow I had equal amount of precision and measure this parameter, lensing deflection angle around, let's say, a galaxy, that I should obtain exactly the same type of constraint. I should find that gamma equals identical 1. But it might not be the case. So the outline of this shorter part of the talk is that I'm going to discuss possible non-universality of this parameter with an example of f of r gravity. I'm going to describe how f of r gravity produces a non-universal value of gamma, in that this value of gamma depends on the Newtonian potential of the lensing mass. And then I'm going to discuss how we might be able to probe this non-universality, taking this as just a straw man or as an example of a known gravity theory that has some nice features, in particular that it can explain late time acceleration. And how we might be able to start to probe this by looking at a sample of elliptical lensing galaxies. And then I'm going to present some preliminary results using the SLACS survey, which I'll describe in a moment. So first, just the example of f of r gravity. So this is probably not necessary here, but just quickly, in terms of an action principle, we just define f of r gravity as having the usual Einstein-Hilbert term, and then adding some arbitrary function of the Ricci scalar f of r. And you can show just by looking at the linearized gravity around some source that this deflection angle, this gamma, can be given by this expression here. And we can see that the important relationship in order to determine gamma in this theory is the relationship between the scalar curvature and the energy density of the lens itself. So in general relativity, that relationship between the scalar curvature and the energy density of the lens is fixed. It's an algebraic relationship. Not much interesting is going to occur, and we get gamma equals 1. But in f of r gravity, this relationship is replaced with a differential equation. So you can actually have some fairly interesting behavior going on here with solutions to this differential equation. And in particular, these solutions have two different types of behaviors. If the Newtonian potential of the lens is less than some characteristic value, which is going to be set by the function f and parameters related to it. So if this is true, then what one finds is the solution to this equation implies that the scalar curvature is much less than the mass density of the lens. And just looking at this formula here, if this combination is negligible, we just get gamma equals 1/2. On the other hand, if the Newtonian potential of the source is equal to or greater than this characteristic value, then we have the usual Einstein relationship. And putting that in here, we can see we just get gamma equals 1. So what we've done is we've shown that f of r gravity is an example of a modified theory of gravity that produces a non-universal value for gamma.
For example, so if you have, say, dark matter that has additional scalar component to its self-interaction, so that you kind of make a mistake in the,
when you actually measure the mass
what is mass, really, right? And then you could have
but with that,
just much simpler realization.
With that example, okay, I haven't thought about that example, and I'm sure there are many examples, and that would be, that's a good thing in terms of what I'm about to say, but with that example, would the scalar interaction not contribute to any sort of the dynamical behavior of stars, let's say?
Yeah, you introduce a scalar interaction between dark matter, right? Mm-hmm. So and it's irrelevant within solar system, right? But for the gravitational interaction within the galaxy, right? It will be important.
Okay, right. So that's another example, and another one might be if you look at the details of DGP or some other brainstorm scenario. It's possible that also introduces a new length scale around which we might have a non-universal value for gamma. So the real question is, once we have this idea that gamma is not necessarily universal, can we actually go about probing this and testing whether this universality of this parameter? And we might be able to do that. And this is a proposal put forth by Cyrus Zia in terms of measuring gamma by looking at lensing galaxies. And I'm just going to walk through how we can do that, what observations we need to make in order to do that. So first of all, we need to directly measure the velocity dispersion of the galaxy itself. So we can do that by looking at the spectrum. We look at the broadening of various spectral features, and that allows us to measure an observable velocity dispersion, sigma observed. We also, given that this galaxy that we're imagining is a strong lens, we can get measurements of both its redshift and the redshift of the source itself. So that's how those parameters come into this expression. And then finally, if in the case that the lens itself is an Einstein ring, we can measure the Einstein ring radius, and that allows us, through observable quantities, to determine a value for gamma. Now, the actual analysis is a lot more complicated because there are degeneracies that you might worry about. This is a very simple model that just looks at a singular isothermal sphere for these galaxies. But the actual analysis takes into account an undetermined power law for both the behavior of the luminous and total matter density, as well as a possible anisotropy in the stellar velocity dispersion. So that's taken into account in this analysis. And this analysis has already been done for the SLAC survey. So the SLAC survey stands for Sloan Lens ACS. That's the Advanced Camera for Surveys on Hubble. And they've done this for 15 elliptical galaxies. And this was presented in a paper by Adam Bolton et al. So the data and measurements made by Adam Bolton and others is shown here. So on the y-axis, I'm just showing the gamma ppn. And on the x-axis, I've just plotted it as a function of redshift of each one of these galaxies around which you could measure gamma ppn. Now, first of all, the error in each measurement is about 30%. This error is dominated by our uncertainties in the observed velocity dispersion derived from the spectra. So there's an interesting question in my mind. What would we gain? Is it possible to get more precise observed velocity dispersions? And here I've just plotted one as a reference line. Another interesting thing about this data, and I think in the company of theorists, this will be more interesting than in the company of observationalists. But even without squinting, I think you can agree that it appears as though these data points are congregating along two different distributions. One of them a bit below one of them a bit larger than one. And you can actually be more precise than that than just squinting at this thing. You can do a Kolmogorov-Smirnov test, and you find that if you test the hypothesis that all of these points come from a single Gaussian distribution, you find that that hypothesis is rejected at the 1 sigma level. So it's not yes?
So all these groups are very optimistic about the error bars, right?
It could be that.
That's
No, absolutely. But the reason why I point this out and what makes this to me more interesting. So here we only have 15 objects, right? By the end of the year, this SLAC survey is going to add another 70 objects to this list. So that we're going to have a much larger statistical sample to work with. And what would be interesting is to consider, first of all, what is a fundamental limit to the accuracy with which we can measure this gamma parameter around any one of these given objects? And secondly, what types of statistics, what kind of games can we play with this data? And in particular, attempting to correlate gamma with the local environment, such as the number of nearest neighbors, the richness of the cluster, essentially its environment. Because a lot of these theories will predict a gamma that not only depends on properties of the object that they're looking at, but also its environment. So this seems to be a new way of starting to probe that type of dependence.
So, as somebody who has worked with data, I want to say that 1 sigma rejection, I never heard this combination. I always hear alone at 1 sigma level. I never hear it.
Well, so I could have put it that 30% of the time, this type of distribution is reproduced in this Kolmogorov-Smirnov test. I want to see rejection. You know, I'm interested, of course. I mean, that's why 1 sigma doesn't ever connote anything that's significant, right? It's not significant. But the point is that we're going to actually improve and increase this data set by 70 more objects. And so there might be something interesting there. I mean, chances are the errors have been, something is strange, or there's some systematic offset, and these will actually merge. Unfortunately, not unfortunately, but the analysis that the first group that looked at this did is they assumed this parameter was universal and just averaged this entire set. They came up with an amazingly close answer to 1. And you can see why. Because the amount of overlap between these two different what looks like two different distributions is very small. So whatever combined likelihood you're going to make up for this is going to be highly peaked around 1 if you're going to force all of these observations to agree with each other. But my point is that it might be interesting to look at this data set to look for the universality as opposed to assuming it. So in conclusion, so modifications of general relativity force us to revisit standard calculations. They force us to question our assumption just from the PPN expansion that this gamma parameter is some fundamental parameter. They force us to revisit questions about what tests of gravitomagnetism can tell us about gravity. And that these modifications present novel ways to probe fundamental nature of gravity. And this is exciting because I think there are many new probes of gravity that, outside of the standard way that we've parameterized deviations from general relativity, that might tell us some interesting things if we have examples that give that behavior, such as F of R gravity or DGP, such as lensing surveys, double pulsars, the direct detection of gravitational waves, and possibly even tabletop experiments. So that's it. Thank you.
All right, we have plenty of time for questions. Those who are not during the talk. Anybody? Maybe not. All right, well,
Maybe, yeah.
Okay.
So there has been a lot going back and forth in the literature about F of R theories are allowed or not allowed because of the solar system test, and if they are allowed, they are not cosmologically distinct. So if you can tell us a little bit about what's the consensus on that.
Sure. I have my own personal consensus,
Okay,
right?
okay.
So they're definitely allowed. There's a paper that came out not too long ago by Wayne Hu and Iggy Stitsky, which talked about a particular model of F of R gravity that would be allowed in the solar system. The reason it's allowed in the solar system is because you have to ask the question, what is the appropriate background curvature around which to look for your solution in F of R gravity? If you take that background curvature to be cosmological, that's one way of doing it, and you would find, even in their model, you would find that solar system tests would be violated. But what they demand is that the background curvature in the galaxy corresponds to general relativity in the galaxy. So with that demand, they place some constraints on parameters of their model in order to attain that. But they can then very easily pass solar system tests due to this nonlinear effect that I actually didn't mention the words nonlinear, but if your potential in the solar system, the sun, is larger than some characteristic potential, which now is set by essentially the energy density of the galactic halo, or the mass density of the galactic halo, then you can pass solar system tests without a problem.
Is there any instability in this theory?
No, there isn't. You can choose your function F of R such that you have a stable GR limit, and there is no instability.
I mean, for example, I remember Richard Woodard saying last year in this very room that if you look at the metrics, say, in a massive object like Earth, then it would be unstable.
So I think that's for a particular choice of F of R.
Okay.
That might be the
Maybe
case.
okay.
But there are F of Rs. You have to put a restriction on the second derivative of this function for that to be, I think it's positive. That then gives you a stable GR limit. But, and there are also interesting things about the cosmological implications. It looks like, for the homogeneous expansion, it's just like lambda CDM. But if you look at the behavior of the effective equation of state, it can dip below -1 and come back up, which is similar to some of these double phantom field and regular quintessence. But here you have just one dynamics doing that, traversing W equals -1. So there are still some interesting things that are not, it's not just adding some quintessence, it's not equivalent to that. It's a little more complicated.
Anybody else? How long are you going to be?
So I'm only here until like 5:30.
Okay. This is your last chance.
Or 2:54, I guess. Thank you.